Hello students, today we are going to discuss about the four quantum numbers which is very important. Okay, so our classes, today our lecture number is 3, the module 1 of atomic structure. So let's start the class. Okay students, so now we are going to start the lecture number 3 of the atomic structure, which is module 1. Okay, so these are the some of the course objective of our course, that is our chemistry. The subject code is CH101 or CH201. Credit is 3 and contact hour is 35. So these are the course outcome of our course. This is the lecture plan. So today our lecture number is 3. That is, today we are going to discuss these topics. Okay, now this is the objective of the class, today's class. So today we will discuss in detail the Sommerfeld atomic model. Next, we will discuss about the Zeeman effect. Okay, Zeeman effect means generally if we apply the magnetic field, then what will be the effect of magnetic field on the electrons? Okay, so that we will explain and discuss. And four quantum numbers, which is very important, that also we will explain how we can get the four quantum numbers, and what are the importance, what is the significance of these four quantum numbers, that also we will discuss. Okay, these are the some of the recapitulation of our previous class. uh, Last day we have discussed about the line spectra of hydrogen atom. Generally, the line spectra, how can we get the line spectra? Okay, what do you mean by line spectra of hydrogen atom, that we have discussed. Second thing, we have discussed about the drawbacks of Bohr model. What are the drawbacks? What are the things that cannot be explained by the Bohr's atomic model, that we have discussed. Also, we have discussed in a very brief that what is Sommerfeld model and what is Zeeman effect. Okay, now this is a very quick review. I have given one question, that is drawback of, you have to tell me the drawbacks of Bohr's atomic model. For that, you will have the 10-second time. Just memorize whatever I have taught in my previous class. Just remember that thing and tell me what are the drawbacks of, just one drawback you have to tell me. Yeah, your 10-second time is over. And you are absolutely right. That is, the Bohr's atomic model cannot explain the further splitting of hydrogen line spectra. That means in presence of magnetic field, the hydrogen line spectra will be splitted further, will be splitted in a sub energy levels. Why? This cannot be explained by the Bohr's atomic model. So this is one of the drawbacks. Another drawback is Heisenberg, according to the Heisenberg uncertainty principle, we know that position and angular momentum of an electron we cannot calculate simultaneously, which Bohr's already done. So this is one of the drawback of Bohr's model. Again, Bohr's model is simply applicable for the single electron system, not the multiple electron system. So these are the some of the more drawbacks of Bohr's atomic model. Another drawback of Bohr's atomic model, according to the Bohr's model, the electrons are revolving around the nucleus in a circular orbit. Okay, which is not the actual case. Okay, so these are the some of the drawbacks of the Bohr's model. Now this is the line spectra. First of all, we have the Zeeman series. Zeeman series means while all the electron will jump over in the n equals to 1 level, this energy level. That time whatever we are getting the atomic spectra, the spectral lines, that is called by Zeeman series. If the electron will come to the n equals to 2 energy level, that time what will happen, the series is called by Balmer series. Next, if the energy level is 3, that means all the electron will come to the energy level 3. What will happen, that time whatever series we are getting, that is Passon series. And fourth one is the bracket series. That means the n equals to 4, the energy level, while the electron will come to the energy level that is 4, that time whatever spectral line we are getting, that is called by bracket series. And next we have the Farn series, while the energy level will be n equals to 5, so all the electron will come to the energy equals to 5. That time this spectral line is called by Farn series. So these are the some of the line spectra that we are getting from the hydrogen atom, and this line spectra can be explained well from the Bohr's atomic model. Now one more thing, if we apply some of the magnetic field here, what will happen, the energy levels are closely spaced, splitted in a very closely spaced lines. So these splitting cannot be explained by the Bohr's atomic model. Okay, so these are the some of the drawbacks. Already I have told you the Bohr atomic model is for only the single electron system. The Bohr's orbit is circular, but not it is not the actual case. The Heisenberg uncertainty principle, we cannot know the position and momentum at the same time, which is impossible according to the Heisenberg. But this is also one of the this is also one of the drawback of Bohr's atomic model. Okay. Also, it cannot explain the Zeeman effect. Zeeman effect means splitting of the spectral line in presence of magnetic field, and also the Stark effect, which is we have in presence of the electric field. Okay, so these are the some of the drawbacks of Bohr's atomic model. Now this is our today's topic, that is Sommerfeld atomic model. So Sommerfeld atomic model, according to this model, the electrons are revolving around the nucleus elliptical path, and also in the orbit circular path. Okay, if it is revolving around the nucleus in a elliptical path, what will happen, the position every time, you can see, because we have two axes, one is major axis, one is minor axis for a elliptical orbit. So what will happen, every time the position and the angular momentum will be changing for the electron, which is not taking place while the electron will be around the revolving around this circular orbit, because the radius for a circle is everywhere will be the same, only the momentum will change. So elliptical orbit, if we have the elliptical orbit, that time the position and the momentum will be changed for an electron every time. And for this, we have introduced one more quantum number, that is azimuthal quantum number or angular momentum quantum number. Now, question is, what is this quantum number? What is the importance of this quantum number? Actually, quantum numbers generally are very important for a electron, for an electron. It's like a address, okay, an address of the electron. So the position of the electron cannot be only defined by the principal quantum number, which we have got from the Bohr's atomic model, that is our principal quantum number n. Okay, but to sort out the Bohr's atomic model, the problems of the Bohr's atomic model, the Sommerfeld suggested that the elliptical electrons are revolving rather the elliptical orbit than the circular orbit. If we consider the elliptical orbit of the electrons, that time, every time its position and momentum will be changed, and excuse me, for that we have to introduce one more quantum number, that is azimuthal quantum number or orbital angular quantum number, which is denoted by the L. Okay, and the value of L is n minus 0 to n minus 1. That means if n equals to 4, n equals to 4, then what are the values of L we have? The values of L will be 0, then we have 1, then we have 2, and then we have 3, because the L value will be n minus up to n minus 1. Okay, so that is why the if n equals to 4, that means the 4 energy level, n equals to 4, that means this is the principal quantum number, the energy level of an electron. Okay, so that energy level will be further subdivided into 0, 1, 2, 3. That means some of the sub energy levels also we have also including with this n equals to 4. Okay, and which is denoted by the azimuthal quantum number or angular quantum number. Is this clear to all? Very important concept that you have to find out. Okay, that this 0, 1, 2, 3, that are denoted by the s orbital, p orbital, d orbital, f orbital. Okay. So, this subshells possess slightly different energies. Now, according to the quantum mechanics, what will be the value of this L? That is mvr equals to root over L into L plus 1 into h by 2 pi. Okay, so this is the value that we get from the quantum mechanics. And the angular momentum of the electron moving in an elliptical orbit, very important, elliptical orbit, not the circular orbit. Okay, that is kh by 2 pi, where k is an integer except 0. Okay, the k value will be 1, 2, 3, 4 and so on. The length of the major axis by length of the minor axis. This n by k, that is equals to length of the major axis divided by length of the minor axis. Why? Because here we are talking about the elliptical orbit, ellipse. Okay, so that is why we have also here major axis and minor axis, and that is n by k. Okay, and with increase in the value of k, ellipticity of the orbit decreases. When n equals to k, then the orbit is circular. while the k value, whatever integer elliptical, for the elliptical orbit we have incorporated the k, whatever integer value it is, if it is similar to the value of the principal quantum number, that time the orbit is, we can conclude that the orbit is circular. Okay. The new quantum number is replaced by L, which I have already told you that that is called by azimuthal quantum number or angular momentum quantum number, and the value is L equals to k minus 1. Okay, or if it is if we are denoting it by the n value, that means L equals to, that is 0 to n minus 1, n minus 1. Okay, now look, if our value is n equals to 4, the principal quantum number is 4, that means how many sub energy levels that we have, that is n equals to 4, that means L equals to 0, 1, 2, 3. These are the 4 sub levels we have. So these are the 4 sub levels we can name by it, like while L equals to 0, that is our s orbital. S orbital, that means the circular orbit. S orbital means the electrons are revolving around the nucleus in a circular path. Okay, while L equals to 1, that is indicating the p orbital. P orbital, that means p orbital, generally what is the shape of p orbital? That is a dumbbell shape. Right, exactly. So this is the, while the L equals to 1 value, and that indicates it is the p orbital. The electrons are revolving around the nucleus in a p orbital. While it is L equals to 2, it indicates the d orbital. And while the L equals to 3, that indicates the f orbital. Understand? So thus, according to the, if we follow the Sommerfeld atomic model, so we have only one energy level. That energy level will be subdivided into 4 energy levels, that is S, P, D and F. Understand? So if the electron will be revolving around the nucleus through a circular orbit, that time the energy levels will be further divided. Okay, now come to the effect, that is the Zeeman effect. So for the Zeeman effect, we have to again introduce one at quantum number, that is magnetic quantum number. This should be the small m. Okay, magnetic quantum number. This is magnetic quantum number. Magnetic quantum number, generally what will happen, we are checking that if we apply the magnetic field, so what will be the condition of the line spectra. So this will be the condition of the line spectra. What will happen? Look here. At first the L equals to 1 and L equals to 2. Okay. So at first we have these two energy levels. Now we are applying the magnetic field. We are applying magnetic field. So what will happen? You can see these energy levels further splitted in 3 energy levels. This L2 further splitted in 5. 1, 2, 3, 4, 5 energy levels. Okay. So that is why there will be the possibility, so many possibility of the transition of electron. The electron can come to here, the electron can come here, the electron can come here. Okay. Previously what will happen, only one option we have, this was option. Okay, the electron will move here L2 to L1. Now after applied the magnetic field, the energy levels are again divided. Okay, the orientation, like L equals to 1 orbital orientation, there will be 3 orientation. For L equals to 2, the orbital orientation will be 5. So the possibility of changing the electrical orbits, changing the orbits for an electron will be higher. That is why for this type of so many, you can see so many transitions we can have. That is why what will happen while in this uh, atomic spectrum, in this hydrogen spectra, if we apply the magnetic field, these lines are again subdivided, very closely spaced lines. We can see why, because the lines, the energy levels will be again subdivided. The that is why the possibility of transition will be higher, and that is why we are getting so many closely spaced line, and ultimately we are having this type of band. Okay, the energy levels are so close. Okay, so that, because you can see here these energy levels, between these energy levels the energy gap is very low. That is why the energy levels, the splitting of energy levels will be very close, and which seems to us as a band. Okay, so by this Zeeman effect we can explain that why we are having the closely spaced energy levels. Now for this again we have to incorporate another magnetic quantum number, another quantum number, additional quantum number, that is called by magnetic quantum number. Okay, now we will check the quantum numbers. Quantum numbers actually a very important, number is very important for electron, which is the address. Already I have told you which is the address for an electron in an atom. So we can know the energy level, the type of orbital, the orientation of the orbital, and the orientation of the electron also. All these things we can know if we know the quantum numbers of the electron. Understand? Every electron in an atom will have a unique set of quantum numbers. Exactly. So every electron should have the unique set of quantum numbers, because these electrons are negatively charged. Okay, so that is why if they are not having the unique quantum set of quantum numbers, that time repulsion will take place. That time the atomic stability will be destroyed. So that is why unique set of quantum numbers is required for each and every electrons. Okay, there are total 4 number of, already we have discussed that 4 quantum numbers already we got. First of all, from the Bohr's atomic model we got the principal quantum number, that is n. Okay, so next we have seen that to sort out the drawbacks of the Bohr atomic model, we have introduced the Sommerfeld atomic model, and for that we incorporate the orbital angular momentum or azimuthal quantum number. Okay, which is denoted by L. Next, we have seen that in presence of magnetic field, the energy levels are divided, again divided, splitted into further very closely spaced lines. So for explaining that, we have the magnetic quantum number, which is ml, and the last one is the spin quantum number. What is spin quantum number? Spin quantum number means in a in an energy level, there are two electrons, there will be two electrons. Okay, so if the one electron, the rotation of one electron will be the clockwise, then must be the second electron should have the anti-clockwise rotation, otherwise the atom won't be stable. Okay, So principal quantum number n describes the energy of an electron, the most probable distance of electron from the nucleus that we can determine by the principal quantum number. The number of subshells, how many that principal quantum numbers are incorporating with how many subshells, that we can know from the azimuthal quantum number or orbital angular quantum number. And that is also denoting the shape orbital, like s orbital is circular or sphere, p orbital is dumbbell shape. Okay, so these are the different shapes that we can know if we know the value of the L, that is azimuthal quantum number. Okay, from the magnetic quantum number, it describes the energy levels, how energy levels are, what are the orientation of the energy levels, how energy levels are subdivided. Like for the p orbital, we have three orientation, that is px, py, pz. For d orbital, we have five orientation. In presence of magnetic field, the d orbital, the possible orientation of the d orbital will be five. One is dxy, dyz, dxz, dx square minus y square, and d z square. So these are the five orientation. For f orbital also, again we have the seven orientations. Okay, so all these we can know from the magnetic quantum number. That means if we apply the magnetic field, then what will be the further division of that energy levels. And the spin quantum number, from the spin quantum number we can know what will be the rotation of the electrons. Okay, so this is principal quantum number, that is n equals to 1, 2, 3, that can be n equals to 1, 2, 3, okay, and so on. Next we have the azimuthal quantum number. Already I have told you, that is the L. If L value is if L equals to 0, that means we have s orbital. If this is L, okay. Acha, if L equals to 1, we have the p orbital. If L equals to 2, we have the d orbital. L equals to 3, we have f orbital, and so on. Okay. Okay, and the penetration, the orbital penetration effect will be the size of the orbital will be like this. F orbital means that means the electron will be very far away from the nucleus, the size of the element will be high. Okay, s orbital, the one electron is in s orbital, that means the electron is in very close to the nucleus. Okay, this is the azimuthal quantum number. You can see L equals to 0, that means the spherical, that is the s orbital. This is the dumbbell shape, that is p orbital. Here we have L equals to 2, that means the d orbital. We have generally the 5 d orbitals. Okay, and L equals to 3 if it is, so this is the f orbital, which we have the 7 orientations. So L value, what is the L value? L value will be 0 to n minus 1. That is the azimuthal quantum number. Okay. Next is the magnetic quantum number. Generally that is ml. What is the value of ml? That is minus L to 0, 0 to plus L. That means minus L to plus L. We have the value. Okay, and total value is 2L plus 1. This number divides the subshells into individual orbit, and that the total is 2L plus 1 orbitals in each subshell. Okay, so magnetic quantum number, generally magnetic quantum number, we can know the orientation. like s orbital. For s orbital, what is the magnetic quantum number? That is 0. That is degeneration, C equals to 1. For p orbital, ml value is -1, 0 and +1. Here you can see the three orbitals, px, py and pz, three orientations you can see. Okay, and look here, this is called nodal point. That means here we don't find out any electrons. Okay, these two dumbbell shape, this region, in these two region, only the probability of finding electrons is very high, understand, and this is called nodal zone. Okay, this is the three orientations in presence of magnetic field. For d orbital, we have -2, -1, 0, +1, +2, 5. The degeneracy is 5. The 5 orbitals we will get. And for f orbital, we have ml -3, -2, -1, 0, +1, +2, +3. Okay, the degeneracy is 7. So 7 numbers of orientations that we will get from the so this is from the magnetic quantum number. Now spin quantum number, as I told you, in an energy level, if two electrons are there, one electron will rotate clockwise and other electron will rotate anti-clockwise. These two spin quantum number, this is called spin quantum number, which is plus half and denoted by plus half and minus half. Okay, sometimes it can be also called by up and down. Yeah. Okay, so these are the quantum numbers. Look here, you can have from this portion, you can have this type of question. If your n value is given 2, so what will be the value of azimuthal quantum number? What will be the value of magnetic quantum number and spin quantum number? So you can have this type of question. Okay, so I have given here some of the examples, a table for understand, if you have for your understanding, ki if the number is n equals to 4, that means L value should be 0, 1, 2, 3. So based on this value, again we have the ml value. What is the ml value? That is for 0, that is 0, that is s orbital. For 1, that is p orbital. So for 1, we have 3 orientation, -1, 0, 1, that is p orbital. Okay, 2, that is d orbital, -2, -1, 0, +1, +2, and for 3, that is f orbital. Okay, so we have 7, -3, -2, -1, 0, 1, 2, 3. So all this, just check this one, very easy. If you have the concept of 4 quantum numbers, very easy. Okay, from this portion you can have, you are given one element, so you have to find out the 4 quantum numbers for that atom, for that electron in the atom. Okay, so this type of questions are very common. Okay, now like this type of question I have also here, as for example, I have given one example, that is what quantum numbers are necessary to describe the electrons of 3p orbital. This type of question you can have. 3p orbital, 3, that is n equals to 3p orbital means n equals to, that is 3. P means what? P means L equals to value. Yeah, if n equals to 3, that means L equals to L equals to what will be the value of L? That is 0, 1 and 2. Yes, absolutely right. For 0, the M value will be 0. Okay. Yeah, if 3 L for L value, that should be -1 and plus up and minus up. These are the 3 electrons, because look here, 3p orbitals, in 3p orbital we have 3 orientation, px, py, pz. That means in 3 orbitals we have 2 electrons. That means total 6 electrons we have. In 3p orbital, we have 6 electrons. So, for each and every electrons, you have to find out what will be the value of L, M and S value, because N value is the same that is given. Okay. So for each and every electron, whatever total electrons we have, for each and every electron you have to find out the value. Understand? So these type of questions are very common. That's why I have given here. Okay, now this is the last topic of our class. So now again we are recapitulating whatever we have discussed today in this class. That is, we have discussed in detail, that is the Sommerfeld model. Next we have seen what is the magnetic effect. If we apply the magnetic field, what will be the effect on the energy levels, that we have seen, that is called by Zeeman effect. And also the 4 quantum numbers we have seen, which is the address of an electron in an atom. Okay, so this is very important. Okay, from this portion you must have so many questions in your exam. So please follow the classes and read the study materials properly. That time only whatever assignments I have given you, you can do the assignment. Okay, so thank you students, and see you in the next class.